on to solving problems in rational inequalities. First, we have this illustration. So, in solving rational inequality, interval and set notation are needed. Please refer to the table below for examples. So, we have here the interval notations. So, we have A, B, or your ordered pair enclosed in an open and close parenthesis. So this is the set notation, meaning the x is an element of such that your x is greater than to A and less than to B. So when we try to graph that, so we have A here, so your first part of the interval, and then B here as your second part of the interval. So we have here a denotation in your graph, in your line graph, number line, which is unshaded circle. So that means that these two, A and B, are not part of the whole solution set. So that means that values A and B cannot satisfy the rational inequality. So we have now interval notation, A, B, enclosed in bracket. So meaning again that in set notation, x such that x is greater than or equal to A and less than or equal to B. That means in your graph, you have again A to B as your set interval. This time your A and B is in the form of shaded circle. That means they are part of the solution. So equals A, that equals B. Another, we have A, B. The A is enclosed with a bracket and your B is enclosed with only a parenthesis. So this time, your x notation is x such that x is greater than or equal to A and only less than to B. So this time, the only solution, the part of the solution is this interval A. So the B is not included as part of your solution set. So this time, it's vice versa. So we have A enclosed in parenthesis and B enclosed in bracket. So this time, your B is greater than or equal to, your x is less than or equal to B and greater than to A. So we have A with unshaded circle and B with shaded circle. This time, next interval notation, we have A, infinity. So these are both enclosed with parentheses. So meaning your set notation is x such that x is greater than A and less than to infinity. Meaning in a graph, we have an A as part of your interval to infinity. So continuous up to positive infinity. So in here, your A is not included because this is unshaded, because it's not equal to, your x is not equal to A. Next, we have A enclosed in a bracket, A, infinity, enclosed in parentheses. The infinity, take note, the infinity is, the positive or negative infinity is always enclosed with parentheses because it's continuous. We don't have a limit there. So we have now x such that x is greater than or equal to A and less than to positive infinity. So this time your A is part of the solution set, so it's shaded. Next, we have negative 8 to negative infinity to positive B. So B. So we have set notation x such that x is greater than to negative infinity or less than to positive B or B. So in here, B is enclosed with just parentheses, meaning that this is not included as your solution set. So just unshaded circle. Next up, we have negative infinity, B enclosed in a bracket. So meaning this time, x is less than or equal to B and greater than to negative infinity. So this time your B is included, so it's already shaded circle. And last, we have negative infinity to positive infinity as interval notation. That means in set notation, your x such that x is greater than to negative infinity and less than to positive infinity. So this is the graph. So it's a continuous from negative infinity in this number line to positive infinity. So we have here the steps to solve problems involving rational inequalities. So first, after you get the rational inequality from the given problem, make the right-hand side of the inequality to 0 by additive inverse. So by making that equals to 0, your right-hand side equals to 0, that means that is already in standard form. So next, we need to simplify the left-hand side of the rational inequality of the given rational inequality. Simplify and get the factors. Third, determine the meaningful numbers that will divide your number line to generate the intervals of the possible solutions. So from our previous lesson, we defined that meaningful numbers as critical points, that they are also the same. They are the same terms when it comes to our rational inequality. So we need to determine that by using those after we get the factors of our numerator and denominator. So for the fourth step, we have here testing the intervals. So those key numbers, you can get intervals there. So we have again a table. You can use a table. So in here, we need to know if your intervals are the meaningful numbers, a certain that makes your interval is part of or can satisfy our rational inequality. So again, we have here in the table test intervals, your intervals with your key numbers or your meaningful numbers. Then we have here the test point. Again, it's in between the interval. Should be part of the interval. So in between our test intervals. So next we need to evaluate your numerator and the denominator. So in here, we're just considering the sign for us to get the sign of the quotient. For the next fifth step, so after testing those intervals that you've got, consider only the intervals that will satisfy the rational equation or inequality. The answer will depend on the inequality symbol used. So if it's less than or equals, you can determine that the right side is negative. So if it's right side, it should be greater than. Okay, next. So this is the last step. We need to determine if the meaningful numbers that we have had are already included in the solution set through substituting to the inequality. Again, so after that, you need to express the answer in interval notation. So if they are included, you need to use a bracket notation. If they are not included, you just need to use parentheses, open and close parentheses.
So let us have examples in solving problems involving rational inequality. So let's solve the given rational inequality x over x plus 1 less than 2. So in solving rational inequality, we have 6 steps. First step, we need to make the right-hand side of the inequality 2 be equals to 0 by additive inverse. So we need to get the standard form. So in order to do that, we need to minus or subtract 2 to both sides of your inequality to make this side equals to 0. So 2 minus 2 is 0. So we have x over x plus 1 minus 2 less than 0. Second step. We need to simplify the left-hand side, this one, of the rational inequality. So how? By getting the LCD and then simplifying your, expanding and simplifying your inequality. So we have LCD, which is x plus 1 because we have just a constant here wherein the denominator is just 1. So we have x plus 1. So x here, then minus 2 times multiply the LCD x plus 1. Less than 2, 0. So simplifying this, so we have x minus 2 times x, we have 2x, then negative 2 times 1, positive 1, we have negative 2. All over x plus 1 less than 2, 0. So x minus 2x rather, we have negative x. So 1 minus 2, that is negative 1. So minus 2, constant then, x plus 1 less than 2, 0. So for the third step, we need to determine the meaningful numbers that will divide the number line to generate the intervals of the possible solutions. So where can we get the meaningful numbers? So we have here the factors to your numerator, which is negative x minus 2 and then x plus 1. So we just need to equate these two factors to 0 to know the meaningful numbers. So we have negative x minus 2 equals to 0. So let's transpose this negative x to the other side to make it positive x. So negative 2 equals to positive x. So this is your first meaningful number. Second, we have x plus 1 rather equals to 0. So x equals to, transpose positive 1 to the other side, we have negative 1. So this is the second meaningful number or the critical points. So let's draw the number line here. We have negative 4, negative 3, negative 2, negative 1, 0, positive 1, positive 2, positive 3. So we have negative 2 as here first x, so we have here. Then negative 1, so we have here. So that means this number line is divided into 3. So this first, second, and third. So we have 3 intervals. What are those? So this interval, negative infinity to negative 2. And then this interval, negative 2 to negative 1. And then negative 1 to positive infinity. So those are, we are going to use that in the fourth step, which is testing the intervals. So we can write the table. So we have the four intervals here, then the test points. Third, evaluate. Evaluate what? Your numerator and denominator. And for the last part of the table, we have to get the sign of the quotient. So let's have first the first interval. We have negative infinity to negative 2. Second, we have negative 2 to negative 1. And third, we have negative 1 to positive infinity. We'll just extend it. So now let's have the test points. Where can we get the test points? So the test point should be part or in between the testing intervals. So in this interval, we can make negative 3 as our test point because it's it's in between this interval. So from negative 2 to negative 1, we can use negative 1.5. And then last, we can use 0. So this time, we are going to evaluate the numerator and the denominator with these test points. So we are substituting these test points to the value of your numerator and denominator. So first, let's have negative 3. So negative 3 minus 2. That is equals to negative 3, that is positive 3, minus 2, that is positive 1. So for the denominator, we have x plus 1. So negative 3 plus 1. So that is equivalent to negative 2. So what is the sign of the quotient? So we have positive divided by negative. This is negative. Next, test point, we have negative 1.5. So negative 1.5 minus 2. That is equals to negative 0.5 because positive 1.5 minus 2, that is negative 0.5. Then we have negative 0.5 plus 1. This is equals to negative 0.5 also. So negative 0.5, then negative, or divided by negative, that is equals to positive. Next, we have 0. So negative 0 minus 2, this is equivalent to negative 2. So 0 plus 1, we have positive 1. So negative divided by positive, this is equals to negative. So, for the fifth step, after testing those intervals, the 3 intervals, consider only that intervals that will satisfy the rational inequality. So this one, this rational inequality. So we can get this simplified rational inequality. So we need to depend to the symbol, inequality symbol. So less than to 0, that means it's in negative values or in negative range. So we can use this first interval and the last interval. This negative, infinity to negative 2, and negative 1 to positive infinity. For the sixth step, or our last step, determine if the meaningful numbers, this negative 2 and negative 1, are included to our solution set, to the solution set of our rational inequality. How? Through substituting these values to our inequality. So let's make use of this simplified to get to know if they are part of the solution. So for x is equals to negative 2, let's substitute it to negative x minus 2 over x plus 1 less than 0. So negative 2 minus 2 over negative 2 plus 1. Let's check if it's less than to 0. So negative 2, that is positive 2, minus 2, that is 0, over negative 2 plus 1, that is negative 1. So 0 divided by negative 1, that is also equals to 0. So 0 less than 0, this is wrong. So meaning this negative 2 is not part of our solution. Next, meaningful number, we have x equals to negative 1. So let's substitute to our simplified rational inequality. We have negative 1 minus 2 over x, rather substitute it with negative 1 plus 1 less than to 0. So negative 1, that is positive 1, minus 2, that is negative 1. Then negative 1 plus 1, that is 0. So anything that you divide to 0 is undefined. Meaning, negative 1 is also not part of the solution. Therefore, the solution set in interval notation is this one. So this is our solution set. Therefore, this is our solution set. So we have x, your first interval is negative infinity to negative 2. So it's just enclosed with a parenthesis because it's not part of the solution. And or union with negative 1, comma, positive infinity. So it's also enclosed with a parenthesis because negative 1 is not a part of solution. So this is the solution set. For the given rational inequality, which is x over x plus 1 less than 2. So that's it for solving problems in rational inequality.